Alright, hello everyone, welcome. This is going to be pretty short, just like this quiz. Just an overview of what I'm going to be expecting for our quiz. It's going to be Tuesday for the Honors and Scholars, and I believe it's going to be Wednesday or Thursday, depending on odd or even for my regular chemistry class. This will be pretty similar amongst all the classes. Um, the quiz itself, I'll just be making a few minor corrections um, for each level, but it's generally pretty similar material, and I just like to go over it. This study guide is relatively same, whether it's honors, scholars, or regular. You're going to have the same types of questions. First one is just going to be physical versus chemical change, and all you really need to know is that a physical change does not change up our bonds. If you start off with a molecule of water, H2O here, and you end up going from, let's just say you have a solid, you have ice, and you go to water. You have not changed the molecule. You have the same exact bonds. This makes it a physical change. But if you go from H2O, and you break this thing down, like this, technically you should have another oxygen, but you've broken this bond. This bond has been broken, and this bomb has been formed, so you've changed something. You end up with H2O, 2O. It's really, we want it to be technically correct. I'll write that. We'll go over that. We'll talk about balancing. You will get this. Alright? So, that is the gist of it. Physical change breaks bonds, or does not break bonds. No bonds are broken. Chemical change breaks bonds, forms new bonds, etc. Okay? Your second question is going to be getting a chemical formula from a chemical structure. So I'm just going to pull this up here. This is a counting game. So here you'll see examples like this on the homework. You'll see an example like this on the quiz. Alright, all you have to do is count how many atoms of each element there are. I don't care what order you put them in. I will do what's most oftenly seen. Let's count our carbons. 1, 2, 3. C3. Let's count our hydrogens. I'll use a different color. 1, 2, 3, 4, 5, 6, 7, 8. And we just have the one lone oxygen. Again, I don't care what order you put them in. I won't take off. If you put OH8C3, not going to take points off. Okay? But this is really just to reinforce what a structure is, what a formula is, and what these subscripts mean, and the coefficients. Here are our subscripts, and this kind of tells you that there are 8 atoms of hydrogen in this entire molecule, and 3 atoms of carbon. Now, you might be asking, what is this thing over here? This is the same molecule. So instead of writing out, we could just also write C3H8O, same molecule. Or because there's 2 of them, instead of doing all this, we're going to put a 2 out in front. There's our coefficient. And this tells us that we have 2 of these molecules. Here's 1, and here's 2. So don't forget that coefficient. Don't give me this. Because there are no bonds. No bonds. Alright, these are not connected. They are 2 separate molecules. They happen to be the same, which is why we write the 2 in front of them, but don't double it up like that. We need a coefficient. Okay? You will see an example just like this on your quiz. Alright, last 3 questions on whether a chemical equation is balanced or not. There's a whole bunch of different examples that we can go through here. I'll do some from the homework. Let me go here. Okay, so this is just from the homework, and all you're really looking for is your products and your reactants. you need to start off on the left-hand side. So I'll do, I'm going to start off with this example here. Here's our reactants. So I'm going to use R for our reactants. And you're just going to tell me how many atoms of each element there are. So I'm actually going to zoom in. Cool. So here's our R for reactants. And let's start with our hydrogens. To get our hydrogen, we take our subscript times our coefficient. 2 times 3 equals 6. 6 hydrogen atoms. We don't have a coefficient, so it's just a 1. And we have 2 nitrogen atoms. Let's go on over to our product side. Here is our products. I'll use a different color here. We take our subscript times our coefficient. We have 6 atoms of hydrogen. And 2 times 1 is 2 atoms of nitrogen. Okay, so these numbers are exactly the same. This 6 matches this 6. This 2 matches this 2. This is balanced. That's all I'm looking for here. I do want to show just a few caveats, just some of the examples that you may kind of see. So here is a reaction. This is a double replacement reaction, which we'll get to. And for a lot of this, just for my regular chemistry students that are watching this, we're not gonna. I'm not including any of these parentheses, but the rest of this you should be able to do. So just most of this you'll be able to do, just a small amount that I'm not going to be asking of you. Okay, so let's start off with our reactants. I've labeled reactants and our products here. So let's start off with our potassium. So I'm going to split this down the middle just to show you here which side is which. So we have potassium, we have nitrogen, we have oxygen, we have aluminum, and we have chlorine. So we have a lot going on in this reaction, which gives us a lot to really work with. So let's take potassium here. We have 2 times our potassium. There's no subscript. We only have 2 potassiums. Again, with nitrogen, 2 times just the 1 here. It's going to give us 2 nitrogens. And for oxygen, 2 times 3 gives us 6. Okay, let's move on to the aluminum chloride. We have 2 times 1 will give us 2 aluminums. 2 times 3 gives us 6 chlorine atoms. So again, what we're doing is multiplying the coefficient by the subscript. Here is our coefficient. I'm going to put a box around it. This is our coefficient. And I will put this triangle around our subscript. That didn't work. That's alright. I'll make a better triangle. I can't make a good triangle. Perfect. So our subscript is what I put in the triangle. Let's go on to the other side. So here's where things get a little more difficult. But we're going to do the same. We have the same elements. I'll do them in the same order as well, just to kind of really showcase this. So again, let's start with our potassium here. Potassium, there's only 1 potassium. 2 times 1 is 2. So the nitrogen, here's where this gets a little bit difficult. We now have this, we now have our parentheses here, which gives us 2 subscripts. For the case of oxygen, there's a subscript here and a subscript here. So what we have to do is multiply the subscript, both subscripts, by one another, and then multiply that by the coefficient. So nitrogen has this invisible 1 here, so it would do 2 times 1 times 3, and that would give us 6. So there would be a total of 6 nitrogen atoms. For oxygen, now we have this 3. So we'd have to do our coefficient, 2 times this 3 times this 3. And this will equal 18. So the 18 atoms of oxygen here. Alright, aluminum, we go back to just no subscript, so we just do 2. And our chlorine, we 2, there's no subscript, times 1 is just 2. So we can definitely tell our potassiums match up, but, oh, and our aluminums, but that's about it. These don't match up, these don't match up, these don't match up. This is a non-balanced, not balanced, or unbalanced, both meaning really the same thing. Non-balanced, unbalanced, it's not good. Okay? So this is just really what to expect for all of this. You're just doing subscript times coefficient. If you got parentheses, you have another subscript. Okay? The last thing that I'm going to go over is how to recognize and, categorize different equations. So we went over the different types of equations, and I'm just going to show you the tips and tricks that I'm gonna expect from you. Here is a synthesis reaction. Okay, they form more complicated from smaller compounds. They smash things together. You have A plus B into AB. So two things that are separated, they come together and form something bigger. So the best way to kind of to really notice this is you will only have the plus sign on the left hand side, like this. No plus signs on the right hand side. So if it's just a plus sign on the left hand side in your reactants, it's most likely a synthesis. So you're combining two things together. Okay? So decomposition, as it says here, is the opposite. They're opposite reactions. Instead of combining two things, you're taking two things and breaking them apart. So if you have something that starts out big and you break it in half, you have a decomposition reaction. And here are your examples here. Notice how you only have the plus sign on the right hand side in the products. So if you just see an addition sign in the products, it's probably a decomposition reaction. Okay? So we have three more. I'm gonna pull this up. We'll talk about a combustion reaction, which is really kind of a special type. So combustion reactions. Now, this whole thing right here, what you're gonna see some kind of carbon thing. Technically, this has a different reaction than I've been using. Reaction of substance with oxygen. But it says hydrocarbons are the most common substances, and that's what I'd really like to focus on. So you're going to see something that's got carbon, hydrogen, and sometimes oxygen, plus O2. And if it's a carbon-hydrogen thing, you will always, I'm doing this vertical to save space, you will see, which we can see right here, CO2 and H2O. So, how to know if you have a combustion? Look for O2 and look for CO2 plus H2O. Alright, this is the most specific type. So this is like a very specific reaction. So if you see these three things, you see CO2, you see H2O, you see O2, and you got something that's carbon and hydrogen, and sometimes oxygen, you got yourself a combustion reaction. Okay? Alright, we now have single replacements and double replacements to finish off with. So I have a reaction here. Reaction of an element with an ionic compound. Most of the time you'll see these with ionic compounds. Not all the time. Just as a heads up. But most of the time this is what you're going to see. This is what we're going to see in our lab this week. Okay? So how this is going to work is you're just going to have you're going to see something on its own plus something that's paired together. Alright, so you're going to see a pair, usually an ionic compound. Not always. You could have something like HCl, which is a lot more, that's more covalent. But you're going to see something that's going to swap with it. So you're going to see two addition signs. So you're going to see an addition sign on each side. Okay? What is this gonna make? You're gonna see an addition sign on each side, and all that's happening here is there's a swap. This magnesium is swapping places with the hydrogen. Now hydrogen is all on its own. So this is gonna be our single. It's single. You can think of it like, you know, not in a relationship. And our pair. And if you want to look at this fun cartoon going over here, okay? So you're going to see something else on its own. We're going to explore this a lot this weekend, or this week. Specific types of single replacement reactions, but you should know you're going to see addition signs on both sides, and you're going to see something on its own on both sides. What I mean by something on its own is just a single element. This H2 is just hydrogen. It's not any other element. It's not, if we want it to be technical, it's not a compound. It's just hydrogen. And lastly, we have double replacement reactions, which again is mostly going to be positive ions for the most part. And you're just going to see your two cations swap places. You have a cation and an anion, plus a cation and an anion, and two ionic compounds, and they're going to swap places. So if we take this example here, let me write this out. Oh, this should be our. This I should be up here. All right. We got space. There we go. Perfect. All right. So our potassium and our lead have swapped places, and now the lead is paired up with the I, with our iodine, and our potassium is paired with the nitrate group. Alright, so polyatomics are split off by their parentheses, so they move as a group. Alright, they do not break up, they do not separate. You're always going to see NO3 stick together in this type of reaction. Okay, the best way to tell a reaction is a double replacement is you have plus signs on both sides, and you have two things that are not on their own. So in the single replacement, you had something on its own, like this aluminum, like this fluorine, like this copper, like this chlorine. In a double replacement, you're always going to have two pairs. So we have potassium plus iodine, and then the lead and the nitrate. So we have two pairs of things that are connected. Nothing is on its own. Alright, these are both ionic compounds. Okay. So that's all for this quiz. I will post the answers to the homework. If we just I'll post the answers to this homework, and we're gonna review it in class as well. But this is just an addendum to what we do in class to prepare for a quiz. All right. So that's all. Have a wonderful time studying.